You ever been in a situation like this?
Floating on flow.
Making my way downtown, walking fast.
Flow.
Faces pass and I'm homebound.
Floating on flow.
Staring blankly ahead, just making my way.
Swag on max, got no legs, bitch, I'm floating.
Hi, my name is Duncan Yee. Fortunately, Babe Penelope are safe as she just had a close call. As you can see, events on the road can be highly unpredictable. This may be from the sudden lapse of judgment between both parties to the unattended baby stroller rolling through the intersection. ICBC statistics show that accidents within a four-way intersection can be devastating. I have initially set out with a team of studious and hardworking students to design a solution that would mitigate the number of accidents within four-way intersections. And this system was designed to be integrated onto the city's existing infrastructure. My responsibility within the group is to develop the machine learning and the image processing subsystem. The component was designed to be able to detect approaching vehicles and to determine its intended path by its turn signals prior to reaching the intersection. As this was a challenging portion of the project, I wanted to isolate the component and to optimize the task. The object detection mechanism integrates the tiny YOLO model with pre-trained weights from the Pascal VOC dataset using the dark flow framework. The pre-trained neural network can detect 20 distinct objects. Once an object is detected within an image, a bounding box will be drawn around it. I have modified the framework to only append objects detected as cars and its pixel location into a list. My initial idea to detect whether a vehicle's turn signal is flashing is to utilize image subtraction. The basis of this technique is that two frames are subtracted between each other. The varying difference between the images of a flashing signal will be accentuated onto a singular image. The vehicle is split into two regions correlating to the location of the left and the right turn signals. Several image processing techniques, including the application of Gaussian blur and a binary threshold, reveals the bright regions of the image. Sufficiently large detected components indicate that the turn signal is flashing. The U.S. Department of Transportation defines a design of vehicle turn signals to flash with a 2 to 3 second period. Frames of detected vehicles are collected with a staggered time frame and loaded onto a queue. The delay is staggered to prevent all of the queued images to contain instances of the signal lights at the on or the off states. To further deter this event from arising, the queue is distributed into retrieved queues, and when a queue is full, the image subtraction algorithm will be performed to all the images within the queue. The majority of detection is used to determine the intended direction of the car. The accuracy with this method is about 24%, increasing to about 42% with retrieved queues. This initial attempt was a crude design with several flaws. Firstly, it is near impossible to provide two images at the same exact location of the vehicle, angle of the camera, and the same background noise to perform the image subtraction algorithm. Any differences between these images will result in detected noise, which may present a false positive. This means that a vehicle must stop at the intersection for this algorithm to work, which ultimately fails to fulfill the intended scope. Secondly, humans aren't perfect. We change our minds all the time. I wanted the algorithm to constantly track the state of the turn signals at each frame in real time. The image subtraction technique was superseded by optical flow, which can be used to track the location of the turn signals while the vehicle is in motion. Optical flow calculates a locally displaced vector field in a sequence of images using Taylor series estimation, which assumes that motions between frames are small. The technique that applies to this problem is the Lucas-Canati algorithm of sparse optical flow. The algorithm tracks pixel locations at each subsequent frame. A counter is attached onto the tracked pixel while the pixel is processed at each frame to determine whether the amber light of the turn signal is on or off. When the turn signal is on, the counter increments positively from positive 1. When the turn signal is off, the counter increments negatively from negative 1. When the absolute value of the counter is within the period of the defined frequency of the turn signal is determined to be flashing. Since the counter is constantly being updated, the state of the turn signals are tracked in real time, even if the driver changes the intent of the direction. The problem that needs to be asked with the optical flow method is, how are the turn signals initially targeted? Several projects suggest utilizing a corner detection method such as the Shitomasi algorithm to estimate the edges of objects, and this produced unpredictable results as the corner detection may not land on the turn signal. My solution to this problem was to append the pixel of every amber-colored object detected within a bounding box of the car into the Lucas-Canati calculation. This seems to work well, however, targeting all amber-colored objects within the car unnecessarily appends pixels, which may produce false positives. My final solution is to implement a supervised transfer learning to retrain the weights of the tiny YOLO model using my own dataset consisting of 238 images to only detect two objects, the car and its turn signals. Since training a model requires a large dataset to detect all vehicles, I provided a small dataset to detect the latest Mazda, Toyota, and Lexus sedans. With the model being able to detect the location of the vehicle turn signals, the corner detection or the color detection method can be localized and accurately applied to the frame. The former method effectively eliminates the dependence of color detection. The object detection mechanism can be enhanced to further improve the accuracy of the determination. Although a larger dataset can be provided, training would require more time. There are several algorithms to optimize the detection, which include boosting, ensemble, bagging, and random forest modeling. Boosting is applied in the proof of concept in an effort to reducing the bias with weaker classifiers.